Alright, today we're going to look at 3 examples of using synthetic division. So, the first one, we've got a polynomial, and we're going to divide it by this binomial. So notice that there's no x cubed term, so this is one of those ones that has a gap that I was talking about in class. So we actually have to put a 0x cubed in there to keep track of the place values as we divide. So to start off with, we're going to do long division just for the first one. We're going to see how it compares to synthetic. So you go through at any point, pause this, convince yourself you know what you're doing. Remember, you're basically dividing, subtracting, and then you multiply the top by the left side. And each time there, you're kind of reducing the original polynomial down into a lower degree polynomial. So at the end here, what we see is we end up with a remainder of 16. And again, like I said, pause that, go through those steps a little slower, and to see how this compares to the synthetic version. So when we do synthetic, we take the coefficients of the original there, so 1, 0, 3, -7, and 2, and what we do is we divide them by the potential root. So in this case, it's 2 because x minus 2 would have had a root of 2. Now the difference here is we multiply instead of divide, and we add instead of subtract. It's much quicker, we don't have to write as many letters down. We end up with the exact same result as what we had before. You just have to know that if that was x to the 4, this new one down here is x to the 3 because we're reducing the degree. So if we were to write the division statement, it would look something like this. And you can just tell, yeah, each degree kind of goes down from there in descending order. So what that is you've got that's like your dividend, your divisor, your quotient, and your remainder. Use p for polynomial, but technically it's the thing that was being divided by, so it's called the dividend. Alright, so we're going to keep that up in the top right corner, call that our division statement. And we're going to try another one here, so number 2. This time we won't have any gaps. So this is a cubic function, and we're going to divide by, let's say, x minus 3. So I'm going to go straight into synthetic, which means we have to figure out what would the root have been. So potentially there might be a root at 3. And this is a big part of this chapter, actually. I'm going to look ahead in this little video. Put the 3 in there. There we go. And notice there's a remainder of -39. When you get a remainder that's not 0, what that means is that that root is not actually a root of the equation. You guessed that it might have been, that's why you divide it, but it turns out that it doesn't actually work out as a root. So you can still write the division statement. All that happens is you have a remainder of -39 at the end. And just to reiterate, because this is a big part of the chapter, we kind of guessed that x equals 3 might be a root, but it turns out that it's not, because we ended up with a remainder that wasn't 0. Alright, and the last one here, so we've got a power of 4, degree of 4. We won't do gaps again, and I'm going to kind of hint at what's coming next. So see how there's a -12 at the end? What we might want to divide by is all the potential factors of 12. What this is, these are potential roots that could work. This is something called a rational root theorem that we'll do later. I'm going to choose 2 because it's an even number, 12. I could choose plus or minus 2. I'm going to go x minus 2, which means my root would have been 2. I plug my coefficients in, and I'm just going to check. And because I checked this question beforehand, I know that this works out to have a remainder of 0. Now what that means is I made a good guess because I tested it beforehand, and x minus 2 is a factor then, and x equals 2 must be a root because we got a remainder of 0. It also helps us, it takes our degree of 4 polynomial, we've worked it down to a cubic, so if we write our division statement, it's going to look like that, and notice there's no remainder this time. There you go. And what we could do is you could take that and you could try to reduce that further to find the other roots. And just to give some terminology for the sections that are coming up in this chapter, in the blue there, that's called the rational root theorem, when you sort of guess at potential roots. And this thing about the remainder being 0, there's kind of two theorems there. They're called the remainder theorem and the factor theorem. So much more on those later. And thanks for watching.